Okay, we are discussing about pumps. Okay, last week we covered positive displacement pump part, and today we will try to cover this rotordynamic pumps. Okay, under rotordynamics pumps, we can discuss about centrifugal pumps and jet pump, gas lift pump, and hydraulic ram pump. Okay, so in last week we discussed these things: damper pumps, gear pumps, okay, then vane pumps. We all discussed. Okay, today part I will start from this slide. Okay, so today I will try to discuss rotary dynamic pump, rotordynamic pumps. Okay, so rotordynamics pumps, we can categorize uh, where the fluid is moved by a rotating element known as impeller. Okay, then the rotating element is impeller. Impeller mean this type of part. Here you can see a impeller. Okay, these are impellers. Okay, so this centrifugal pump deal with impeller. This this all rotor dynamic pumps have an impeller that is driven by an engine or a motor. Okay, this all pumps have, all rotor dynamic pumps have an impeller. Okay, so this impeller, this impeller is crucial for the pump's operation. Okay, then the flow is governed by the hydrodynamic action, which means that the fluid motion is controlled by the forces resulting from the rotation of the impeller. Okay, these are centrifugal force and other forces. Then, then energy transfer mean one of the key characteristic of a rotordynamic pump is the continuous high-speed rotation of the impeller. This rotation adds kinetic energy to the fluid, which is the converted into a pressure energy. Okay, so Okay. Then continuous high-speed rotation of the impeller adds kinetic energy to fluid. Okay. This is the energy transferring method. Okay. Then according to that one, rotating element is impeller. Okay. Uh, this impeller like heart of the rotordynamic pumps. Okay. Then this impellers have various designs such as radial, axial, mixed type. Okay, I will show. These are different impeller designs. This one radial one, the mixed one, and axial one. Okay, we can see different type impeller in industry. Okay, here you can see centrifugal pumps. This part is motor and this is the impeller. Okay, here you can see a casing, and inside of the casing you can see a impeller part. Okay, this impeller coupled with this motor. Okay, so these are centrifugal pumps. Okay, centrifugal pumps, they are the most common type of rotordynamic pumps. Then according to that one, we can say in industry they use these centrifugal pumps for a lot of applications. Or you can see various applications using these centrifugal pumps. Okay. Then it has rotating impeller within a casing. Here you can see casing and this impeller fixed with this casing. Okay. So flow enters axial through the eye of the pump. Okay. Flow enter from this side, from this hole, and flow drain from this side. Okay, then it's mean this side we can say suction side, and this side we can say a discharge side. Okay, this is the discharge side according to this diagram. This is the discharge. Okay, this is the suction. Okay, using this real pump, you can see this is the suction line connect to this pump. This area you can connect discharge line. Okay, this side inlet side, this side outlet side, discharge side, suction side. Okay, Then centrifugal pumps are widely used in industry because their simplicity, efficiency, and ability to handle wide ability to handle a wide range of fluids. Okay, then they it can handle liquid with low viscosity. Then we can use this type of pump, centrifugal pumps, as applications. We can use water supply system, chemical processing, for sewer treatment plants. Okay, we can see lot of applications. Then important thing is this impeller. Okay, this impeller typically made of metals. Okay, metals, so composite materials. Um, then design to im then design to impart kinetic energy to the fluid. Okay, this design of the impeller including the number and shape of the its blade. Okay, here you can see uh, number of the plates and shape of the plates. Okay, here you can see blades. Here you can see 1, 2, 3, 4, 5, 6 blades here. This one we cannot see other side in this impeller. Okay, this is the back side, this is the front side. Okay, this shape is effect to our pump performance. Okay, then it will affect to suction head and discharge head in our pump. It's mean power of the pump. Okay, this shape of the impeller blades affect to power of the pump. Okay, then pump housing is designed to contain the fluid being pumped and to convert the kinetic energy imparted by the impeller into pressure energy. This casing guides the fluid to the discharge point. Then this casing also a very important thing. This inlet part, inlet part, sometime you can see eye. Okay, so you can see in some books uh, they use eye as a inlet part. Okay, this is central part of the impeller, this part. This design allows the fluid to be drawn into the pump smoothly. Okay, this design uh, allows to uh, move pump smoothly, then minimize turbulence and maximizing efficiency of the pump. Okay, then fluid uh, fluid moves radially outward through outward through impeller blades. Okay, then water enter from this suction side. Then impeller will rotate and this fluid go through this arrow line. Here you can see. Okay, due to centrifugal forces. කේන්ද්‍ර අபிසාරි බලයනේ centrifugal force. Then the fluid then move radially outward through the impeller channels. Okay, then this is the method inside of the you can see inside of the pump, centrifugal pump. Then this type of pumps uh, ability to handle variant type of fluids. Okay, variety of fluids. Then maintenance cost is little bit low comparing with other pumps. Maintenance process is easy comparing with other pumps. Okay, then we can discuss their operating principles and how they convert kinetic energy to pressure energy. Okay, and using this part you can identify how convert kinetic energy to pressure energy. Okay, then kinetic energy generated by using motor. Okay, then when the impeller this impeller when the impeller rotates it imparts a spinning motion to the fluid. The fluid particles are plunged outward due to centrifugal force, causing the fluid to move radially from the center. Okay, then as the fluid moves through the impeller channels, its velocity increases. The kinetic energy imparted to fluid by impellers is converted into pressure energy. Then this conversion occurs because the cross-section area of the flow path within the pump increases as the fluid moves outwards. Okay, then decrease increase pressure according to Bernoulli's principle. Okay, then here you can see a spiral shape casing. Okay, this is a very important thing. It will affect to convert kinetic energy into pressure energy. as the fluid leaves the impeller, uh, it enters the volute, okay, where the gradually increasing cross-sectional area slow down the fluid and increase its pressure. Then another thing is this design, this spherical design, sorry, spiral design uh, helps helps to guide this water fluid, okay, water fluid, and this spiral design also minimize uh, losses inside of the path. Okay, these are the cases. Using this diagram, you can identify how to fluid going through this path. Okay, here you can see blades, impeller blades. Okay, this is the suction point, suction pipe line. This one, discharge line, outlet line. This is the inlet location. This is the outlet location of the centrifugal pump. Then understanding of this operating principle, then it will helps to identify operation and maintenance, and also you can select required pump. Okay, according to your requirement, you can identify a pump type. Okay, so here you can see a different type of impellers. Okay, these are different types. Here you can see impeller blades. Okay, in this case also shape is shape is different, but process is same. Okay, here you can see blades, impeller blades. In this case also you can see impeller blades uh, in between these two plates. Okay, between two plates you can see here fixed with blades. Okay, here you can see inside of the these two plates you can see impeller blades. Okay, then different type of impellers. You can see radial impellers, mixed flow impellers, and axial flow impellers. Radial impellers, mixed impellers, axial impellers. Okay, these are casing. Okay, it is spiral shape one. Okay, then radial flow pumps are used for high heads and relative low flow rate applications. Axial flow pumps. Axial flow pumps are used for high flow rate with low heads. Okay. Then I will okay. Uh, okay, here I will draw some diagram. I will pick one pump here. Okay, this is a pump. Okay, I need to bring I need to pump water from below tank to top tank. Here I will fix below tank. This is top tank. Okay. Then you can fix pipeline like this. Okay. Then this this is this is a suction line. Okay. Suction or inlet line. This is a discharge line. Then what is the meaning of uh, head? Then they told us radial flow pumps are used for high heads. Axial flow pumps are used for high flow rate with low heads. You know about flow rate, Q value. Flow rate mean Q. What is the head mean? Head mean this height. Okay. Then high heads mean according to this height, we can say head of the pump. Okay. Head of the pump is high. Okay. We can pump this uh, then using head you can identify pumping height of the pump. Okay. තොට ඔයාලට මේ හෙඩ් කියන එකෙන් පම්ප් කරන හයිට් එක තමා මේ හෙඩ් කියන එකෙන් එන්නේ. හරිද? අපි අර P බෙදීම රෝජී කියලා එහෙම ගත්තා නේද හෙඩ් එක ප්‍රෙෂර් හෙඩ් එක කියලා ගත්තා. ඊට පස්සේ V වර්ග බෙදීම 2G කියලා එක ගත්තා. V square divided by 2G කියන්නේ velocity head නේ. අන්න ඒ වගේ තමයි මෙතන මෙන්න මේ හෙඩ් එක තමයි මේ කියන්නේ. එතකොට high heads කියනවා radial flow වල. If you use a radial impeller, then you can take high heads, high height. Okay, you can take a little bit larger height. You can use. Uh, then axial flow. When you use axial flow pumps, then height should be low. Okay, you can pump to minimum heights. It's how can I say? Uh, this pumping height is really small comparing with radial flow pumps. Okay, then mixed flow pumps operate between these two extremes. Okay, the mixed flow pumps we can operate uh, for these two purpose. Okay, high flow, low heads, and high heads, low flow rate applications. Okay, then here you can see another type of centrifugal pump, double suction pipe centrifugal pump. Then in this case, in this case, uh, this pump, this double suction pump features a pair of impellers arranging back-to-back configuration. The water discharge from each impeller is directed into a spiral casing. Here you can see spiral casing. Then due to its superior design, these are this is the inlet. Okay, this is the outlet in this pump. Due to this design, this pump is used for various industrial applications. Okay, engineering applications. Uh, then we can take high head. Okay, high head and high flow rate using this double suction centrifugal pumps. Then these impellers are positioned back to back. Okay, here you can see impellers are positioned back to back. Then inside of the pump, we can see fluid enters the pump from both sides of the impeller. Okay, both side of the impeller. When using this pump, you can take high flow rate and high head. Okay, good flow rate and high head. Then this type of pumps mainly used in water treatment plant, HVAC system, power generation, process. It's mean this type of impeller use for power plant. Okay, power plant. Then you can see large scale industries. Okay, you can see this type of pump in large scale industries. Then due to use this type because they use this type of pump because flow rate is high. We can create high flow rate and also high pressure. Okay, then efficiency is good. These are the cases we need to select this double suction centrifugal pump. Okay, these are advantages. Then as advantages, we can take flow rate is high. Good flow rate we can take using this pump and high head. Okay, so here you can see multi-stage centrifugal pumps. This centrifugal pump consists with consists with few impellers. Okay, then here you can see multiple impellers mounted on a single shaft. Okay, here this one shaft. These are impellers. Okay, this is the casing of the pump. Here you can see outside, then you can see cross section of the pump here. Using this speaker, you can identify cross section of the pump. Okay, this is the inlet, this is the outlet. Okay, suction here, discharge here. Okay, this is the design. Then this multi-stage impellers fixed with this single shaft. Okay, then each impeller increases the pressure of the fluid. Then you can get high head using this pump. You can create high head. Okay, then comparing with single impeller centrifugal pump, this head is very large. Pumping head is very large. Pumping height is very large. Okay, then due to this each impeller increases the pressure of the fluid in stages, every stages. Okay, then this pump allow for high head applications in industry. Then we can take high pressure using this pump as advantage, and these are used in boiler industry. Boiler feed water into process, and also use cleaning systems, then high pressure cleaning system. This is a good pump for it. Okay. This this arrangement is series. Okay. This impeller arrangement is series. And also separated by some casing part. Okay. All are separated by some casing part. Here you can see. You can watch a video, then identify how to arrangement of multi-stage centrifugal pump. Okay. You can see several impellers, and these impellers fixed with the Seagull shaft. Okay. Then fluid moves through each stage of the pump. Its pressure increase uh, uh, pressure increase gradually. Okay. Then each impeller adds energy to the fluid progressively build up the pressure. Okay. Then we can generate very high pressure using this pump. We can use high pressure applications. Okay. Due to this, generate high pressure ability, ability to generate high pressure. Here you can see centrifugal pumps, submersible pumps, centrifugal submersible pumps. Okay. Then why need a centrifugal submersible pump? Why need a centrifugal submersible pump? What is the application using? What are the applications? What's the meaning of submersible pump? Can you explain about submersible pump? What are the things do you know about the submersible pump? Have you seen submersible pump in industry or any location? Yeah, submersible pump in underwater pump. Yeah, this is a fully submerged pump. Okay, then then Other centrifugal pumps installed in installed above ground. Installing above installed above ground. Okay, then submersible pumps. This centrifugal submersible pumps are placed directly in the fluid. Okay. Then this design eliminates the need for priming and reduces the risk of cavitation. Then here you can see like a well. Okay. Then pump you can fix here inside of the water. Okay. Then this is the suction line, outlet line. Okay. Then you can fill to a tank here. Then after that, using another pump, another centrifugal pump, you can pump this water to other purpose. Okay. Then here you can see large submersible pump. Okay. Then here inlet, and this is the outlet. Here a suction area, then discharge pipe here. You can see. Then fluid enters the pump through uh, through an intake located near the bottom of the unit. Okay. The impeller then adds kinetic energy to fluid, kinetic energy to fluid and to the fluid which is pushed upward through the pump and out through a discharge pipe. Okay, the submersible pump is allows for efficient fluid movements uh, as there are minimum losses associated with suction lift. Then these type of pumps we use for various applications to pump sewer, okay, uh, waste. We can pump using the submersible pump and water well we can pump. Then commonly used for groundwater from well for agriculture, industrial, and residential use. Okay. Then we can control flood areas using this submersible pump. Okay. And then flood control, then flooding control. These are the applications. Here you can see other features in submersible pump. Okay, under submersible pump. Then we can see several important features, several other important features here. Okay, then first one is double volute pump. Minimize the load on bearings and a shaft due to unbalanced pressure dis- distribution around the impeller. Then minimize then double volute design incorporate two volute chamber within the pump casing. Okay, here you can see two volute chambers. Okay, these are two. Then this design helps in distributing the pressure more eventually around the impeller. Okay, then by balancing the pressure on the both sides, uh, the double volute pump reduce the axial thrust expressed by the pump shaft and bearings. Then advantages, these features minimize the risk of shaft and bearing damage. Okay, then leading to improve pump reliability. It also helps in reducing noise and vibration during operations. Okay, this will affect to vibration in our pump. This design is effect to vibration of the our pump. And also then unbalanced pressure distribution around the impeller. Then impeller pressure balancing. Then impeller pressure balancing also very important thing. Okay, here you can see holes in the impeller balance the pressure in the both side of the impeller. Here you can see two holes. Okay, there are two holes top of the impeller. You can see. Okay, through this impeller. Then this will help to balance pressure uh, in both side of the impeller. Okay, then these holes allow fluid flow through and balance the pressure on both sides of the impeller, and then reducing unbalanced forces. This also effective damage of the bearing. Okay, then according to these holes, we can reduce the damage of the bearing and also vibrations. Uh, because we can see we cannot see uneven pressure inside of the pump. Okay, this balancing mechanism helps to smooth operation of the pump. Then and also reduce uh, wearing wearing parts and pump shaft bearings, all thing we can protect according to these was this pressure balancing work. Okay. Then self-priming pumps are designed to handle the initial removal of air from the pump and the suction line without requiring external assistance. Okay, this is a mechanism that allow the pump to create a vacuum and draw the fluid into the pump casing automatically. Okay, self-priming means that then when you are going to start pump, then you can start pump without fluid using this self-priming pumps mechanism. Okay, then as advantages, then this mechanism helps to simplify of operations in our pump. Then it is very easy to use. Then pump is very easy to use, and then no need to no need to uh, no need to manually enter fluid inside of the pump before start the uh, pump. Okay, then these are the additional features in centrifugal pumps enhance their performance, efficiency, and reliability. Okay, then you can select right pump. Okay, required pump according to this these specifications and these features. Okay, you can select your pump according to your requirement. Okay, then here you can see pumping system. You can see a pumping system. Okay, in this area reservoir. Okay, you need to pump this water uh, to this location, top of the top tank, to this top tank or top reservoir. Okay, then this is the piping line you can identify here. This is a foot valve. Okay, then here suction pipe, you can see suction pipe fixed with the pump. Okay, here you can see a centrifugal pump, and this is the suction pipe connecting a point here. Okay, then here you can see discharge line, outlet line. Okay, this is the inlet one, this is the pump outlet. Okay, this one called as a discharge pipe. Okay, then here you can see check valve and also bends, different bends, elbow here, 90 elbow here. Okay, then this head you can get as a static suction head. Okay, this part suction, this vertical head. Okay, not this angle height, you should measure this vertical head, static suction head. Then from pump height to above, this pump height to above height you need to get as a discharge head. Okay, no need to consider this angle one, you need to consider this, okay, vertical component of the height. හරිද? එතකොට ඔයාලා මේක ඇන්ගල් එකේ දිගේ හෙඩ් එක නෙමෙයි ගන්නවා. සක්ෂන් හෙඩ් එක කිව්වොත් මේන්න මේ හෙඩ් එක තමයි ගන්නවා. ඒතකොට රිසර්වර් එකේ ඉඳන් පම්ප් එකට. පම්ප් එකේ ඉඳන් අවුට්ලට් එකට තියෙන එක. කියන්නේ මෙතන වතුර අවුට් වෙන්නේ. මෙතනින් තමයි ඉන් වෙන්නේ. වතුර අවුට් වෙන තැනට තියෙන එක තමයි ඩිස්චාර්ජ් හෙඩ් එක. හරි? ඒත් මේ පම්පින් ලයින් එකේ තියෙන ඔයාලා කතා කරා ලොසස් එහෙම අපි කතා කරන්නේ 90 එල්බෝ එකකින්ද ලොස් එකක් වෙනවා. මෙතන එල්බෝ එකකින්ද ලොස් එකක් වෙනවා. ඒ වගේම පයිප්ලයින් එකේ ෆ්‍රික්ෂන් එක හින්දා ලොස් එකක් වෙනවා. We can see a different type of losses inside of the pipe path. Okay, due to this elbow and due to this friction inside of the pump, we can see different losses. Okay, when you are going to design this pipeline, then you need to consider these things, losses and pump head, everything you need to check and calculate. Here you can see the base mounted one. Okay, not a submersible one. Here you can see a surface area, then surface mounted centrifugal. Here you can see a below surface mounted one, but uh, motor is surface mounted one. Okay, using a concrete tank like a sealed area. Okay, without any water here, we can't see any water here. Then a sealed tank, like a sealed tank. Okay, then here you can see water reservoir, and we can see here pipeline. Okay, this is a pump. This pump coupled with this motor using this shaft. Okay, here you can see a small coupling here, and the valve also coupled with a shaft, and this is a pipeline. This is the discharge line. Here you can see suction line. Okay, then below surface area you can see, you can fix this type of pumping line. If you want to fix this type of pumping line, you can fix. Okay, then suction level also same level. Okay, here in this case suction is below, suction inlet point is below to pump level. Okay, in this case suction level is same. Okay, then in this case discharge level, discharge head you can calculate according to reservoir level and this outlet height. Okay, මේකෙදී අපි බැලුවේ suction inlet එක මෙහෙනේ තියෙන්නේ. එතකොට ගත්ත reservoir එකේයි pump එකේ ගත්ත suction head එක කියලා. හරි, මේක discharge head එක. මේකෙදී suction head එකක් නැහැ නේ. මොකද suction එකයි suction එක මෙතන තියෙන්නේ. suction එකයි pump එකයි දෙකම එකම ඔසෙන් තියෙන්නේ. එතකොට එතන suction එකක් නැහැ. හැබැයි discharge එකක් තියෙනවා. ඩිස්චාර්ජ් එක ගන්න වෙන්නේ අපිට මේක වතුර පිරලා තියෙන ලෙවල් එකට වෝටර් ලෙවල් එකේ ඉඳන් තමයි ඩිස්චාර්ජ් එක ගන්න වෙන්නේ. මෙතනත් අපි සක්ෂන් එක ගද්දි මේ වෝටර් ලෙවල් එකේ ඉඳන් ගත්තේ මෙතන ඉඳන් නෙමෙයිනේ. එතකොට මේ වෝටර් ලෙවල් එකේ ඉඳන් තමයි සක්ෂන් හෙඩ් එකම යන්නේ. ඒ වගේම ඩිස්චාර්ජ් එකේදී වෝටර් ලෙවල් එකේ ඉඳන් ඩිස්චාර්ජ්. මේකෙදි ඩිස්චාර්ජ් එක විතරයි තියෙන්නේ. ඔයාලට මේ දෙක පැහැදිලිද සක්ෂන් ඩිස්චාර්ජ් කියන එක? එතකොට පම්ප් එකේ ඉන්ලට් එක පම්ප් එකේ අවුට්ලට් එක. මේකේ පම්ප් එකේ ඉන්ලට් එකයි පම්ප් එකයි එකම ලෙවල් එකේ මේ තියෙන්නේ. හරි. එතකොට සක්ෂන් හෙඩ් එකක් නෑ. නමුත් ඩිස්චාර්ජ් හෙඩ් එකක් තියෙනවා. එතකොට මේ පම්ප් එකේ සක්ෂන් මොකුත් නෑ. සක්ෂන් වලට පවර් එකක් වය වෙන්නේ නෑ. නමුත් ඩිස්චාර්ජ් එකට තමයි ආ පවර් එක යූස් කරන්නේ. Okay. Here you can see jet pumps. Then here you can see footwell and suction line. Okay. Then the pump, jet pump here you can see, and discharge here. Then this type of jet pump designed for designed designed for take high velocity. Okay. Then this operate on the principle of fluid jetting. Then here you can see like a nozzle. Okay. Then high pressure fluid stream is directed through a nozzle to create a jet. This jet creates a low pressure zone that throws additional fluid into the pump. Then the mixed fluid is then expelled through a diffuser where it slows down and increasing pressure. Okay, jet pumps are commonly used for water wells and irrigation process, irrigations department, and some industrial processes. Okay. Okay, these are the applications, this type of jet pump. Then we can increase pressure using this jet pump. According to low pressure area, then draws in additional fluid. Okay, creating a low pressure area that draws in additional fluid. Then I will show you a video regarding this jet pump.
A jet pump is used to...
Can you hear a voice in this video voice? Can you hear video voice?
lift liquid from
Can you hear my voice? How about video voice? You can't. Can you hear this video?
a well. A specially designed jet is engineered to utilize
Yes.
Okay, now you can hear. Okay.
a jet pump is used to lift liquid from a well. A specially designed jet is engineered to utilize the Venturi effect. The Venturi effect is a drop in fluid pressure that results when an incompressible fluid flows through a constricted section of pipe. In order for the jet pump to begin working, it needs to be primed. To prime a typical jet pump, it needs to be completely filled with water. This includes filling the pump casing as well as the suction and drive lines. Once the system is primed, a centrifugal pump is used to push the water out. Some of the water is discharged while the rest is recirculated into the drive line. As the water enters the nozzle, it is forced through the venturi. This creates a vacuum which draws the water up from the well through a foot valve. As the water passes through the venturi tube into the suction line, the pressure is increased sufficiently to force the water back into the pump impeller. The foot valve is a crucial part of the system. It is mounted below the pump at the bottom of the well. It is the first mechanical component to contact the water in the well and performs a number of key functions. 1. It receives water into the system and feeds the pump.
Here you can see a foot valve. This is like this one like a non-return valve. Okay. In this area you can see return.
2. It filters the sediment and debris out of the well and keeps it away from the pump. 3. It maintains the pump prime and prevents the pump from running dry. It also prevents the backflow of the water from the system back into the well.
Then a gas lift pump and then a gas injection to lift fluid from well. Okay, here you can see. And then gas okay, then here you can see gas inlet. Okay, compressed air inlet here, this line. Then gas is injected into the well using this pipeline. Then the injected gas decreases the density of the liquid column in the well, then allowing the fluid to be lifted to the surface more easily. Okay, like this. Then these type of pumps are widely used in oil field industry. Okay, for lift crude oil. Okay, crude oil. Then basically oil industry. Okay. Yeah, this using this video you can identify okay, man. This type of pumps are very special pumps. No need to study deeply. Then you need to take an idea about the what is the gas lift pump and jet pumps. Then next pump is ram pump. Okay, here you can see a ram pump. Then you can see this is the reservoir. Then okay, then here you can see a suction part. and this is the outlet discharge part. Okay. Then a storage tank here. Then you need to pump water from this location to this storage tank. Okay, this is a ram pump. This pump utilize the energy of flowing stream of water pump a small volume of water to a high elevation. The flow of water into the pump cases the ram or piston to ramp or piston um, to move, creating a pressure such that force some of the water to be lifted through a discharge pipe. Okay, that's the applications. We can see this type of pump in irrigation or water supply, and also we can see this pump on pump in small scale hydropower plants. Okay, then these are the applications. Then okay, then here you can see a video regarding this ram pump.
Today let's learn how a ramp pump works with the help of this animation.
This pump consists with non-written valve.
Of how it exactly works. So watch the entire video to understand it. Ramp pumps are actually used in hilly areas where we have a source of water from uphill and we need to supply the water also to the uphill area. So here you can see here we have a pool of water from uphill and the ramp pump is over here which is located downhill and we need to supply this water towards a village or a house uphill. So let's see how it actually happens. The water comes into the ramp pump like this and it enters the ramp pump and we have valves inside the ramp pump. So you can see that valve or that getting closed and that valve is the waste valve over there and it gets closed and the water enters the ramp pump over there and the pressure increases due to the gravity. The flow of water from the pool uphill is getting into the ramp pump and the pressure increases inside the ramp pump which result in the water to move up. So you can see the delivery valve opens up and the water moves upwards and it still continues to move upwards which pressurizes the air inside and due to the pneumatic pressure you can see it further get pressurized to a particular level and then that pressure acts back on the water. So when it acts back on the water it pushes the water outside through the delivery uphill. You can see the water is pushed uphill and this cycle continues and that's how the water is being supplied uphill. So this is the process what's happening. Once after the water is being delivered you can see inside the ramp pump the pressure drops and as the pressure drops the valve opens up. You can see the waste valve is getting opened up and the water is being spilled outside. So when the water gets spilled outside, the cycle continues. So now let's say the internal working of the ramp pump in close up and identify the components. So there's the ramp pump. So that's the inlet where the water is coming inside due to gravity. There's the waste valve over there. Then we have the delivery valve. That's the pressure chamber and that's the delivery pipe. So let's see how it works. So the water is entering from the pool. You can see from the pool due to gravity water enters into the ramp pump and it closes the waste valve there. So the waste valve is getting closed over there and due to the gravity and the pressure from the uphill of the pool pressure is increasing inside the ramp pump. As the pressure increases it opens up the delivery valve and water starts to move upwards. You can see there and the air is getting pressurized, pneumatic pressure is happening and to a limit it happens then that air exerts that pressure back towards the water. You can see and that result in the delivery valve also to get closed, and the water is being pumped outside. You can see the water is being pumped outside due to this pressure which is happening pneumatically. So you can understand that there is no external power is required for the functioning of a ramp pump here. It just works due to the pressure from the uphill. The water flows from the uphill due to the gravity, and the pneumatic pressure inside the pump result in its working. And after a particular limit, what happens is that the pressure drops. When one delivery is happening, the pressure drops inside the ramp pump. As a result of this, the waste valve opens up and the water is being pushed outside. So once the water is being pushed outside, again water comes from the uphill, the pressure increases, and the cycle continues, and that's how the water is again and again being pumped. So I believe you got an idea about the working of the ramp pump. So that's how the cycle continues and the pump works continuously. And you can see the basic working principle that we can summarize is that momentum of the flowing water is used to pump the water uphill, and there is no power requirement is there in a ramp pump. And advantage is that no external source of power is required, as I told you, and less moving parts, so less wear and tear is happening inside a ramp pump. The disadvantage is less waste. It wastes a lot of water. As the waste gate opens or the waste valve opens, water is being pushed outside so that fresh amount of water can be taken from the uphill to develop pressure inside the ramp pump so that the next pumping can happen. So it's almost like 10% of the water is being consumed and the other 90% is being wasted through the waste valve in a ramp pump. So I believe.
Okay, then in this part I will discuss about characteristic of pump. Okay. Here you can identify centrifugal pump small diagram. Okay. Then I sketch here. You can identify how to fluid flowing through this pump. Then here you can see impeller of the pump. Okay. Inlet you can see here, and inlet here, inlet like this. Okay. Then parallel to this axis. Okay. Inlet is fluid is entering to the pump parallel to this axis. Okay. This yeah, this axis. Then after that fluid going through this impeller blades. Impeller blades, and according to this impeller cover, according to this spiral cover, then this fluid going through this path. Okay. Then this is the process. Here you can see outlet. Here you can see inlet. Okay. Then here you can see a cross section of the pump. Okay. Using this figure, you can identify a cross section of the pump. Okay. Then this is the impeller, outlet, inlet, Same picture, okay? Same pump. Then using this diagram, I don't know, you can see, can you see these words in this picture? Can you see this? This is a motor, okay? Then here you can fix this motor axis and pump axis using this coupling, okay? Coupling. We can we need to find we require to find coupling according to diameter of the pump and motor, okay? Then here you can see shaft seal, okay? Then shaft seal to seal without moving water. Then this part shaft, motor shaft and pump shaft, okay? Then pump housing here, this ash color one, pump housing, okay? Then impeller blades you can identify. Okay, then inlet flanger here, outlet flanger here. Flanger mean you can fix with another flanger, using another flanger. You can fix a pipe using another flanger here. Then impeller blades, and these are the component in a pump, okay? Here you can see different type of pumps, centrifugal pumps, okay? Inline pumps, it's normal pump, and here end suction pump and double suction pump, submersible pumps, okay? These are the different types of pumps. Then under this lecture series, we need to identify what is the uh, performance characteristic in a pump, okay? In this case, using this video, you can identify how to work performance, how to work performance characteristic in pumps, okay? Then you can identify characteristic of pumps and their head, how to work according to efficiency, okay? Then how can we select good pump according to our requirements, according to our required head, okay? Then these are the things we can identify according to these performance characteristics, okay? We need to study performance characteristic curves, then efficiency curves, head curves, And using this video, take basic understand.
Hey there guys, Paul here from the engineeringmindset.com. In this video, we're going to be looking at pump curves to learn how to read them and what the different lines mean. After you've learned about pump performance curves and the part they play in pump selection, visit today's sponsor, statesupply.com, to find the right pump for your curve requirements, shop for parts, or speak to a knowledgeable pump expert on top brands like Bell & Gossett, Taco, and more. Just click the link in the video description below to find out more. The basic pump curve looks like this, but they do get more complicated and look something like this.
And understanding these characteristics is important for the selection, operation, and troubleshooting of centrifugal pumps. Okay, then you can identify various engineering applications, and after that you can select pump. Okay.
Yes. Don't worry, we're going to go through them step by step and start from the basics. Each type of pump has a different chart, and the data plotted on them also varies with the model. The first thing we notice is that on the main vertical y-axis we have the head pressure, and on the vertical x-axis we have the flow rate. Basically speaking, the head is pressure and the flow rate is how much water the pump can move. So what do these charts represent? If we turn the pump sideways and connected it to a pipe, the pump is pushing the liquid horizontally, so there is no pressure, but the water is flowing at its maximum flow rate. As we slowly rotate the pump towards the vertical position, we see the flow rate decreases but the pressure increases. That's because it's now pushing against the water and the friction. As we get all the way to the vertical position, there is zero water flowing out of the pump but maximum pressure. And that's because it's using all its energy to push against the water and hold it as high as it possibly can within the pipe. At this point, it's just spinning the same bit of water, which isn't good for the pump, so you don't want to run a pump like this in the real world. By recording the values during the elevation, we basically get our pump curve. Although I will note that pump manufacturers don't test pumps this way because it's just not practical. If you want to know how a centrifugal pump works, then we have covered this in detail in our previous video. Do check that out, links down below. Head is shown on the vertical axis, and this is referring to pressure, so we often hear the term head pressure. We measure head in feet or meters, which doesn't seem correct considering we're talking about pressure, especially as you see the pressure gauges on the pump typically reading PSI or bar. The reason for feet or meters is that pump manufacturers only know how high their pump can push a liquid. They do not know which liquid your system will be pumping, and as each liquid has different properties, the pressure will vary depending on the liquid used. However, the height it can be moved by the pump will remain the same. For example, we have this pump which can provide 125 feet of head. If we use it to pump water, the pressure will be around 54.25 psi. But if we were to use it to pump milk, then the pressure will be around 56.15 psi. And that's purely because of the properties of the two fluids. Conversion between feet and meters of head is very easy. We have a free calculator for that, which you can find links to in the video description below. Why do we need to know head pressure? Pumps are usually used to move liquid to a higher region, so we need to ensure the pump can reach this elevation. As we pump liquid through the pipes and the fittings, friction will try to oppose the flow. This occurs from the walls of the pipe, but also disturbances to the flow path. This causes pressure losses which waste energy from the pump. The amount of friction depends on the liquid type as well as the materials and fittings used. Therefore, we must calculate how much friction or pressure loss our system will generate and ensure that the pump we select can overcome this. Otherwise, we're not going to get any liquid out the other end. When we look at the pump charts, we'll find pumps ranging in head and flow rate. For example, when we look at a small domestic heating system, there are a few fittings and short pipes. Therefore, we would use a pump with a relatively low head pressure. But if we were to look at a commercial heating system with multiple air handling units, fan coils, and long pipe lengths, then we know the pressure drop will be much higher, so we would need a pump that can provide much more head pressure. The flow rate is a measurement of how much liquid is flowing from the pump in a given amount of time. This measurement comes in many different units, for example gallons per minute, litres per second, or cubic meters per hour. For example, a system might be designed to move 2 litres of water per second from a holding tank to a process tank. Performance curve. This is sometimes referred to as the HQ curve. H meaning head and Q which represents flow rate. The manufacturer will test each pump to obtain the performance data and then plot this on the graph. This will represent all the possible configurations between flow rate and head pressure, and we use this to check whether a pump will suit our requirements. The performance curve will be different for each pump, and some will suit our system needs better than others. You will usually see that as the pump flow rate increases, the head pressure decreases. When selecting a circulating pump, the pump will only perform as per the line. So, for this model, if we wanted 8 gallons per minute, then we would have 6 foot of head. You can also get multi-speed circulating pumps, which we'll look at later on in this video. When selecting a larger centrifugal pump, as long as our system requirements are on or below the performance line, then the pump can be considered. We can potentially use a smaller impeller or variable frequency drive to better suit our requirements. And again, we're going to look at that a little later in this video. For example, the performance curve of 2 large centrifugal pumps are plotted here. We need a flow rate of 30 gallons per minute and a head pressure of 70 feet. That means that pump 2 can't be used, but pump 1 could be. Impeller size. With centrifugal pumps, we can often change the size of the impeller. The diameter of the impeller will change how much water can be moved. So on some charts, you'll see multiple performance curves, which will give us the performance details of the pump for different diameter impellers. For example, 30 gallons per minute for a 4.5-inch impeller gives us around 13 feet of head. But if we use the 5.5-inch impeller, then we would get around 22.5 feet of head. In some instances, our required flow rate and head pressure might fall between the 2 impeller diameter lines. In such cases, we can often machine the impeller down to the required size to get a better match. You should ask your pump manufacturer or pump specialist to carry out this service though. The performance of the pump will then need to be calculated. I'll leave some links in the video description below for worked examples for that. Pump power. As we know, pumps require mechanical power to spin the shaft, rotor, and ultimately move the water. Pump manufacturers will usually provide a chart which plots the power requirement. In imperial units we use brake horsepower, and in the metric system we use kilowatts. With this chart we see the brake horsepower plotted at various intervals. As you can see, as the flow rate increases, so does the power requirement. We use this chart to size our motor. For example, if we needed 125 gallons per minute with 18 feet of head, then this is between the 0.75 and the 1 horsepower lines. As this point is above the 0.75 line, this means we can't use a motor of this rating because it will not be able to cope. Therefore, we will have to use a 1 brake horsepower motor. And we see the performance curve falls completely under this line. So if our head pressure calculation is wrong, then we do have some safety margin. If you want to convert between brake horsepower and kilowatts, then check out our free calculator, links down below for that. Efficiency. Some charts will display the efficiency curve of the pump. This is measured in percent. We will usually see this curved line where the pump increases up to its maximum efficiency and then it starts to decline again. Charts that display different impeller sizes will usually have efficiency displayed in these more complex plot lines. Each line displays the percentage of efficiency. In both charts you can see that the efficiency varies depending on how you operate the pump. In multiple impeller size charts we see that the efficiency decreases as the impeller size also decreases. And that's because the gap between the impeller and the pump casing increases. And that will allow water to recirculate in this region and therefore waste energy. The efficiency is the ratio or comparison between the amount of energy going into the pump versus the amount of energy we get out of the pump. So ideally we want this to be as close as possible to the peak for optimal performance. The pump will always lose some power when it converts and transmits this electrical energy into mechanical energy. And this will be lost through the couplings, the bearings, the shaft, the seals, the cooling fan, etc. For example, on this chart, we can see that if the pump provided 125 gallons per minute at 25 feet of head, then it would run at around 67% efficiency, which isn't very good. If the same pump operated at 30 feet of head for 138 gallons per minute, then it would operate at its peak performance of 73%, which is much better. MPSH. This is the required MPSH, or net positive suction head pressure. This usually has an upward curve, which means as the pump flow rate increases, we see the MPSH value also increases. We measure this in meters or feet, sometimes kilopascals. The MPSH is the minimum pressure that must be available at the suction inlet of the pump to overcome the entrance losses and avoid cavitation. The available pressure at the inlet must therefore be greater than this value. Pump cavitation is where the pressure at the inlet of the pump reaches a low enough point that the water begins to boil. This creates rapidly expanding and collapsing air bubbles which will gradually destroy the surface of the pump and the casing. For this example, if we were to move 150 gallons per minute, then we would require an MPSH value of around 4.9 feet. Multi-speed pumps. Some pumps, such as this one, operate at a fixed speed and therefore have a fixed performance curve. But we can also get multi-speed versions which have the ability to switch between speed settings. Typically, these come with 3 different speeds: low, medium and high. These pumps will therefore have a chart with 3 different profiles plotted on them. We can operate the pump at any of these curves, but not between them. So, for this example, if we wanted 6 gallons per minute, or 0.3 litres per second, then on setting 1 we would get around 4.2 feet of head. On setting 2 we would get 8 feet, and on setting 3 we would get around 9.8 feet. Variable speed or variable frequency drives. Another option we have is to use a variable frequency, or otherwise known as a variable speed drive. This basically takes the electrical supply and alters it to reduce the voltage and frequency, which therefore alters the power of the motor and the speed of the pump. We can increase or decrease the speed via the controller to better improve our pump match and therefore operate nearly anywhere in the region below the curve. These are only really used on larger pumps, typically over 2 kilowatts in size. They do come pre-installed with new pump motors, or you can also retrofit existing pumps, but you should check with the manufacturer first to ensure compatibility. Additionally, you must check the system design to ensure it can handle a lower flow rate and head pressure. To obtain the performance details for variable speed pumps, we have to calculate the values using the pump affinity laws. We've covered this previously in worked examples, links down below for that. Rotational speed. Some pump manufacturers will provide separate charts for operating the pump at different rotational speeds. We can then compare the performance to get a close match and then find an electrical motor which will suit our needs. Typically speaking, higher rotational speeds lead to more service and maintenance, so where possible it's good practice to choose a lower speed pump that meets our system requirements. Voltage and frequency. Do check the specifications of the electrical motor. The voltage and frequency for mains electricity vary around the world, so we want to ensure that the pump you select will operate where you are installing it. Additionally, pumps come in single as well as 3-phase designs depending on the application. These details will be provided by the manufacturer and usually come on the chart or a technical document. Okay guys, that's it for this video, but to continue your learning then check out one of the
Okay, I think you got idea about the performance characteristic in pumps. Okay, in a pump, centrifugal pumps. Then here you can see graph. This graph for performance characteristic graph. Okay. Then this line indicate efficiency of the pump, and this line indicate head of the pump. Okay, then a maximum efficiency you will get in this point. Okay, then according to maximum efficiency point you can extend this point up to this line. Then you can identify best efficiency point, and then according to this point you can get best head for the pump. Okay, then in this case this axis shown that this vertical axis given head Okay, then this horizontal axis given flow rate Q. Okay, and in this graph, vertical axis represent the head of the pump, then horizontal axis represent the flow rate of the pump. With you can measure using cubic meter per second, liter per second, or likewise. Then head you can measure using meter, millimeter, centimeter, likewise. Then another line is lower speed curve. This red line is lower speed curve. Then okay, this curve shows the performance of the pump when it is operating at a lower speed. As we can see, at lower speed, lower speeds, the head is lower for given flow rate compared to a high speed. I will show you higher speed curve using this blue color one. You can identify higher speed curve. This curve indicates the pump's performance at a high speed. Okay, as the speed increases, the head generated by the pump also increase for the same flow rate. Okay, then these are the pump curves. Then this best efficiency point is a important point on the efficiency curve. It represents the flow rate at which the pump operates with maximum efficiency. Okay. Then at this point, we can identify pump head flow rate and efficiency are ideally balanced. Okay, we can say this in this point, pump head flow rate and efficiency are ideally balanced. So understanding these curves, according to these curves, you can select right pump for your specific applications. Okay. Then you can select the best pump according to maximum efficiency. Okay, using efficiency curve. And also this will effective operation of the pump, and this pump curve important for troubleshooting. Then this will helps to identify issues in pump like cavitation, we are also identify using these curves, and improper installations of the pump you can identify according to these characteristic curves. Okay. Then in this curve you can identify this using this performance characteristic curve, you can identify total head here total head versus capacity. Okay, total head versus capacity. Then horizontal axis is horizontal axis is Q capacity. Then vertical axis is total head. Then here you can see efficiency curves. Okay, efficiency curves. These are efficiency curves. Then here you can see different impeller diameters, 6.5 inches, 8 8.25 inches likewise. Here you can identify different diameters. And okay, then this large impeller diameter generally produce higher heads at given capacities. This one. Okay. Then these are efficiency curves. And these efficiency lines help identify the efficiency of the pump at various operating conditions. And 80%, 70% efficiency. Okay, here 74%. Okay, then BHP. Here you can see BHP. BHP mean brake horsepower lines. These lines, these lines, we can say BHP lines. Then labeled with values such as 3 horsepower, sorry, 3 BHP, 5 BHP, and 7.5 BHP. Okay. Then these lines helps determine the power required to operate the pump at different points on the performance curve. Okay, matching the pump operating point with the available motor power is crucial to avoid overloading the motor. Okay, then here you can see point A, point B, point C in this line. This point A represent high efficiency operating condition for a medium size impeller. Okay, then point B, this point indicate a low efficiency area possible due to suboptimal operating condition or mismatch between pump size and application requirements. Then point C, this point C typically near to the BEP. BEP means best effective point. Okay, where the pump operate most efficiently and effective. So these are the things you should know. Then here you can see specific gravity underneath under this note. Okay, then this indicate that performance curve are based on a fluid with the specific gravity 1.0. Okay, which is typically for water. Okay, then this is especially this will introduce for water, fluid as water. Then using this performance curve, you can select the right pump, and you can design system using this curve, characteristic curves, and you can do troubleshoot. So you can identify issues. Okay. Okay. Here you can see a centrifugal pump. Okay, and you can calculate suction head. Here you can see a suction pipeline connect with the pump in this location. Using this location, you can connect discharge pipeline. Okay, then pump inlet here, outlet here. Okay, then flexible connection mean you know this is coupling. Okay, electrical motor here, then base plate. Then you can calculate a suction head using this equation. Okay, here you can see Bernoulli equation, P over OG plus V square divided by 2G plus Z for suction. Okay, then the discharge also you can calculate using same equation for discharge area. You can apply for discharge pipe. Then effective pump head you will receive using HP. You can reduce HD minus HS. HD mean you can reduce discharge head from suction. Sorry, you can reduce suction head from discharge head. You can reduce suction head from discharge head. Then you can finally you can get effective pump. Okay. Then finally total head supply by the pump you can identify according to head loss plus effective pump head. Okay. එතකොට මෙතන තියෙන්නේ බර්නෝලි ඉක්වේෂන් එක දාලා දැන් මේක හිතන්නකෝ මේක වතුර උඩකට ගෙනියනවා කියලා. ඔයාලගේ තියෙනවා හයි රයිස් බිල්ඩින් එකක් টොප් ටැංක් එකක් තියෙන එකට වතුර ගෙනියන්න. හරි. එතකොට ඔයාලා කැල්කියුලේට් කරගන්න ඕනේ සක්ෂන් එකේ හෙඩ් එක කොච්චරයි. හරි. සක්ෂන් එක පැත්තේ තියෙන හෙඩ් එක කොච්චරයි. ඒ වගේම ඩිස්චාර්ජ් එක පැත්තෙන් යන්න ඕනි හෙඩ් එක කොච්චරයි. ඒ දෙක කැල්කුලේට් කරලා ඒ දෙකේ වෙනසෙන් එනවා ඔයාලා මැද තියෙන පම්ප් එකේ. පම්ප් එකේ තියෙන හෙඩ් එක. හරි. ඒ දෙක ඇතරියම පම්ප් එකේ තියෙන හෙඩ් එක. ඒ පම්ප් එකේ තියෙන හෙඩ් එකට ඔයා එකතු කරන්න ඕනේ තව මොකද්ද? ඒ පයිප් වල හැම ලොස් එකක් තියනන්නේ. පයිප් වල ඔයාලගේ බෙන්ඩ් යූස් කරනවා ඒවයි. ෆිටින්ග්ස් වල ලොස් එකක් තියෙනවා. ෆ්‍රික්ෂන් ලොස් එකක් තියෙනවා. So total head loss එක plus මෙන්න මේ effective pump head. හරි. Then finally you can get this pump efficiency using output power divided by input power. Okay. Output power divided by input power. Okay, then output power mean this hydraulic power, this fluid power. Then input power mean mechanical power. Okay, then output power you can calculate using this equation. Okay, effective pump head multiplied by rho multiplied by G multiplied by Q. Q mean flow rate of the pump. This will given pump power, output pump power. Okay, and you can get output pump power. You can determine by product of the total head, the flow rate adjusted for the fluid density and gravity. Okay, then after that you can calculate pump efficiency. Okay, here you can identify application of Bernoulli's theorem. And next thing is net positive section head. Okay, this part I will discuss in next day. If you have any questions regarding these pumps, you can ask. Please study about centrifugal pumps. Centrifugal pumps, it's very useful pump in industry. You can see variant applications. Okay, can you hear? Can you hear my voice?
Yes, sir.
Okay, I will wind up here. So if you have any questions, you can ask. මොනා හරි ප්‍රශ්න තියෙනවා නම් අහන්න. මේ ස්ලයිඩ් එකත් මොකක්ද වුණා? එතකොට ඔයාලට දැන් ගෙදරම ඉන්නනේ. මේ චුට්ටක් බලන්න පම්ප් කර්ව්ස් ගැන ස්ටඩි කරගන්න පම්ප් කර්ව් මොනවද කියලා. ඊට පස්සේ ඒවයි දැන් මම කැල්කියුලේෂන් පාර්ට් එකක් පෙන්වනවා අන්තිමට. මම ප්‍රසන්ටේෂන් එක ගෙවන්නම්. ඒක පොඩ්ඩක් ස්ටඩි කරන්න කොහොමද වෙන්නේ කියලා. හරි. පම්ප් වර්ගවලින් අර මේ ජෙට් පම්ප් ඒවා නම් මේ ලොකුවට බලන්න ඕනේ නැහැ නිකන් අයිඩියා එක ගන්න ඔළුවට දාගන්න. නමුත් සෙන්ට්‍රිෆියල් පම්ප් එහෙම චුට්ටක් ස්ටඩි කරලා තියාගන්න. සෙන්ට්‍රිෆියල් පම්ප්ස් තමයි සාමාන්‍යයෙන් ඉන්ඩස්ට්‍රියල් ඇප්ලිකේෂන්ස් ගොඩක් තියෙනවා. හරි. අනිත් ඒවාත් තියෙනවා. සාමාන්‍ය ඕනි තැනක සෙන්ට්‍රිෆියල් පම්ප් ගැනනේ ගොඩක් කතා වෙන්නේ නේ. ඔයාලටත් ඇහිලා ඉතින් දැන් ගෙදරක වතුර ගහන්න ගියත් ඔයාලා සෙන්ට්‍රිෆියල් පම්ප් එකක් තමයි යූස් කරන්නේ. එතකොට මේ පැත්ත බලන්න. performance curve බලන්න load curve කියලා හැම තියෙනවා තව ඉස්සරහට. මේ චුට්ටක් ඒ ටික ස්ටඩි කරන්න. එතකොට කොහේ ගියත් බර්නෝලි ඉක්වේෂන්ස් ඒවා පරණ ඉක්වේෂන් ටික යූස් වෙනවානේ. discharge equations flow rate එක කොතෙන්ට ගියත් ඒක fluid වල කතා කරන්නේ. Okay. I can't see any questions issues. So anyway, I will meet on next week. We will meet on next week. Then now I will stop here. So thank you for your support and participation. If you have any questions, you can message to me or ask, okay? Call to me.